fellows. Means the deadline in September, look for some time, you should win each second or six.
Okay.
Make 10 applications, you get three applicants. But in Latvian case, of course, because you need to get to the level of 70 from 100, and then this Marie Curie fellow will be financed through National Structural Fund. Much easier, because the success level for direct financing is 95 or 100. Ashes basis.
Okay, thank you. I think let's leave the questions for lunchtime. And now we are moving to the last presenter, which will be online presentation. Ivan Andronov from Odessa. I think Aigar will help to arrange the technical things, multi-harmonic and special shape pattern template approximations of discrete signals with generally irregular arguments. Okay. Are you ready?
Yes, I'm ready. Do you see my presentation?
Yes, we see, and the floor is yours.
Okay. So, dear colleagues, I'm very thankful to have a possibility to present my talk at your conference. And I would like to concentrate to mathematical methods and to some special shapes which may be used. We apply this for stars, for variable stars, but maybe it will be interesting also to fit some outbursts or other transition processes, so more on mathematics than on physics. So we have a group who applied these methods, and I would like just to remind that there are many types of variable stars, and so 70 at least, and mixes of them. Here we see only 7. But anyway, we see that there is no sinusoidal variation. This is very rare for astronomical signals. And the next that we have data which are irregularly distributed in time. So we may not switch on some device and to have regular data, except for tests for Kepler. But typically for photometric surveys, we have irregularly spaced data. So this is what we have to do instead of oversimplified formula which are there. Such types of presentations, I typically make an epigraph, which I got almost 30 years ago. But okay, I try to say that there should be different methods which are statistically optimal for different types of a signal. Okay, why we use phenomenological modeling? Because, okay, we have hundreds of thousands of stars which have discovered from surveys, from satellites, but only 300 which are studied enough. So they have spectra, they have models, physical models, and so on. So the main idea that we make some parametric or phenomenological modeling which needs less parameters, and so they may be obtained with a better accuracy. Okay, the simplest case, we see the star or the moon and the light, and we can't say which is the luminosity unless we know the distance. So we may not use this. So this is the main idea for these types. So there are 4 main groups which we study in. So starting from global ones, but very often we have just nightly runs, and so there are split physically that we can't observe during the invisibility of star or during the day and so on. But also we work on window approximations. which may be interesting when we have not a strictly periodic variations, but quasi-periodic variations or cyclic variations, and just may see how it evolves with time. And so running approximations, they are overlapped and also interesting to do this. So I have not too much time, so we'll be speak faster. So, okay, we have a small part of the light curve, one of the stars, and okay, even here we have a problem. So where to cut the data? Because if we don't cut, then we have a Gibbs phenomenon, and so there are waves which don't exist and which are just a bias or a fake, if speaking in modern language. So if we cut this, the beginning of the outburst, the end of the outburst, okay, then we have a choice of very many functions which may fit this. Okay, if we want to make a physical modeling, we must know the structure of the star, the temperature, and so on, how it makes an outburst, and so on. Here we speak just on phenomenological modeling, so polynomial of fourth order, asymptotic parabolas, I will introduce them, trigonometric polynomial, and seconds, hyperbolical seconds, which is also fruitful for asymmetric curves. So there are just a very short list of figures just to say what do we use for the weight functions. These weight functions are typically used for smoothing. They may be good for regularly spaced data, so you may see any textbook on this. And so you may see here different functions. So here is Gaussian, and also a seconds hyperbolical second, which corresponds to a logistical regression. So we know that this curve is typically used not by astronomers, but by biologists during an epidemic and so on. So also for COVID, there were such approximations. So having here an exponential rise and an exponential decay, and so here is some maximum which is here. Also, we have used this for running parabola, and we just compared different weight functions to obtain this. So we see that they are relatively good, and for 35 years this year I use the B-square filter with parameter 2 and 2, and so it was used for many of our stars. It is good not only for quasi-periodic oscillations, but also for fractal things and so on. As to fit the maxima or minima for eclipsing variables, of course, everybody who studied mathematical analysis at the first course of the university, okay, there should be a second derivative, which is not zero and not infinity. And so we may have a set of functions which are local. No, okay, they may be scaled and shifted, of course, so which are local, and we may use them. But we see that another approximation is very bad. So here we have also a power asymptote here, but it is bad, for example, for eclipsing binaries, where this beta should be 1.5. So when two circles intercept and we have some minima, then we see here. So we have improved this function, and so you may see a set of this. So there may be flat maximum or minimum. So for example, for transit of the exoplanets, for example, and here everywhere we have an asymptotic behavior which corresponds to two circles which work here. Okay, there is no limb darkening in this model, but this is just to have a good function which will have good roots and so on. However, what are the previous data by other authors? Okay, everything is approximated by a Gaussian. This may be a spectral line, this may be an eclipse, and so what is bad here? The bad is that no sense in Gaussian, which is very useful when we have an infinite number of data, and so continuous data, and then these integrals well work with the Gaussian. However, for the discrete data which we have, no sense of the Gaussian, so we may find something similar. So here we again may see this green line which corresponds to B square approximation, but anyway, no sense of this. And extreme case which may be used by this function is this triangle top, which corresponds to an eclipse of two exactly exactly equal stars. So equal radius, equal brightness, and in this case, the eclipse begins and ends immediately. So this is the function of this. And okay, there may be also other functions which are here. For asymmetric curves, we have here okay, also a lot of functions, but what may be interesting physically? So we try to make models which are not just polynomials, but which may have asymptotes which correspond to physics. So, for example, here is in a logarithmic scale. You see a straight line here, a straight line here. So this may resemble some outburst or okay, maximum of the pulsating variable. So also a shock wave which goes here. And here is some characteristic time of this rise and another time for the fall for the standing branch which are here. And okay, the red line is a typical Gaussian. So you see that it doesn't have constant derivative at the beginning and end of these curves. And okay, how it looks in typical amplitudes or typical intensities. So you see here also the same curves, but not in a logarithmic scale, as we have, for example, stellar magnitudes in astronomy, but just in intensities normalized by a maximum here of 2. So this is what we have done, realized. I just will show some other things. However, okay, 40 years ago, okay, 30 years ago, we had slow computers and so on. So if we want to have here an asymptotic line, and here we have some connection with a parabola, so we have used an asymptotic parabola method. Here are the accuracies and so on, how it may work. For irregular type stars, this is also a phenomenological approximation. And here we have a simple 5-parameter approximation, which has here a square parabola at the descending range, and here a cubic parabola. So here we have the continuous function, its derivative and second derivative. So just for irregular type stars which have very asymmetric curves. Okay, this is general what we work. Now I speak on this part mainly. For more details, you may see this chapter of the monograph, which was published 5 years ago. There are many methods, despite during 5 years, something new was done. So why do we spend time on new methods? Okay, this is the curve from this year. So I have just put here, and so the approximation makes me excited. Okay, the minimum is more or less, but here we don't have other parameters which are here. Okay, this is just some games with the Taylor expansion and Fourier expansion for the data which are not regularly spaced, but okay, you see here how they look. So this is a random distribution, and so we see here a very fake peaks at the periodogram. Also for the splines, so some types of splines, when we just split the complete parameter, complete interval into smaller intervals, and so you see here an example, very bad if we use large interval, better for this right interval because here the derivative is infinite, and okay, here just two lines coincide within 1 pixel. Okay, for the Fourier well-known things, so I would like to say that we use a complete complete form which is in here. So we have C1, which is also dependent on frequency at the periodogram analysis. When we use Lomb-Skargl in its classical view, so C1 is just a sample mean. This is nonsense. We may just see that. Okay, for the number of parameters, there are, of course, ANOVA analysis of variances or the Fisher criterion, but also we use the mean squared accuracy for the fit. So here sigma xc or signal to noise, which we have for different approximations which are seen here. Okay, so this is just formula and also problems which we may have in astronomy. So in the Fourier analysis, there is just a copy, an infinite number of copies right and left of the signal. And so here we may just have some difference, and so the Fourier approximation will go to this and will make a lot of wrong things which are seen here. Other thing that fast Fourier transform, okay, a part of the data are put not to a correct signal, but they are used as a zero or a mean value. So of course the spectrum changes is very, very nice. Also, there was some study we have tried to see what some programs which are popular now for the periodogram analysis are called Lomb-Skargl. They have nothing common with this. This is just an improved version which was made by Ferraz Mello and which is in fact just corresponds to a correct trigonometrical polynomial value without fixing the mean value to a sample mean. So you may see here. So this is the least square approximation, and this is the Lomb-Skargl approximation in two versions which were here. So you see, okay, the mean value during the winter doesn't correspond to the amplitude of temperature variations during a year. But okay, there is a tradition. Okay, you may see here the true position of the coefficients, and here the positions which are randomly spaced, but this is a pure sinusoid which is in here. Okay, the formula are here. No time to do this. Also, how to choose the best number of parameters. Okay, you see here some Cepheids, which we studied with this. And another thing for the approximation is so-called detrending. Detrending means that we have the data, we remove linear trend, and we have the deviations and study them. Okay, the periods are wrong. You see, obviously are wrong because of this detrending. So we have elaborated a program. So this previously it was a Fortran program 30 more years ago, and 20 years ago we made a program which is called MCV, and so you may use it for not only for looking for the data, but also for approximations with trends, multiply harmonics, and up to three periods in this verse. Okay, also there is a remark that I am shocked to see some programs work in periods. Okay, so when you have here the frequencies, it is okay. But if you have periods, so you see that this is inverse, this is simple, but it is nonsense to make a constant step in periods. And for wavelets, of course, it will be logarithms. And also for periodogram analysis, we use not only sinusoid, but also 2, 4, 8 degree of the trigonometric polynomial. Okay, so here we see how the curves and periods changed for 4 stars during the century. So helium, flash, spice, but okay, we see it. Also, we have made a study of the curves, mean curves with the best trigonometrical polynomial, and okay, the phase plane, which is seen here, so closer to physics, so have a magnitude which is lower, sorry, and also have a derivative which we may see here. So something like a heart, and okay, in phase this looks this one. Also, some popular things like Lance's approximation. It doesn't work for good for narrow eclipses, outbursts, and so on. So you see here, instead of this top curve, you see something small with this because it is averaged and it is good only for lower orders of approximations. So, okay, here just we see how it changes. So we must have not overfit like here and not underfit when it is a sinusoid or just a constant, which is in here. Okay, so we try to use the best approximations from the accuracy. And so you see here the number of parameters is 40. And for this is for the best accuracy, and for the Fisher approximation, 44 parameters. So silly to have so much parameters. So this red line corresponds to the accuracy of our specific shapes, which I will show. Okay, this is just to see.
How many time do you need to finish?
I think 5 minutes.
Okay, try to 3 minutes.
Oh, I will try. Okay, thank you. Anyway, it is recorded, so this is just to show and to maybe seen here. Okay, this is not our approximation, but you see it is silly. So the width of the minimum is different from this. Okay, the upper part is okay, but the lower is an absurdum as for me. So we use this shift at scale for looking for these curves. So this what I have shown with the parameter of the eclipse, and you may see that it works good for algos. So we have applied this to a couple of hundred of stars. But what is interesting, it was done for the eclipsing binaries. But also we see that for beta Lyra and W Ursa Majoris, this work also good. And this is contrary to what GKVS says, that if we see the beginning and end, then it's just an algo. Okay, so there are some jumps, and you may see that it is very sensitive to the parameters. So this Python program for the data, you see, makes very different things. Okay, we study many stars from different catalogs, including TESS, and TESS makes us a challenge to improve the accuracy of these variations. Also, I would like to introduce to you, maybe it will be useful to you, and you may just download for free from this site. And so this is all in one. Okay, this is Katerina Andrich who worked this. So there are many types of functions which you may use. Some of them I had shown before. Okay, you may choose which one will make the better approximation. Okay, these are our approximations, two approximations, and this one, okay, from astronomy and astrophysics. It is the best, but it is bad. Okay, so I invite you to this site where you may see. Other that just to use the running sinusoids. So this is also interesting. If we have quasi-periodic oscillations, then it is possible just to see how the amplitude, mean value changes, and so on. We work with this data. And so also finally, I would like to say that okay, we have studied this method of accuracy, bootstrap accuracy, and so you may see how large may be the outlying approximations for the same data. So conclusions, our conclusions are opposite to the referee report, that we do have to have different functions, different methods, or combinations of them to obtain adequate data for this. This is just a memorial talk to my chief, who's pushed me into variable stars. And finally, I would like to invite all of you to our conference, Gamma Odessa UA. Of course, it will be Zoom only because of Russian attacks, 3 damages also this night. So please apply. So it will be soon. So we typically think that it will be this. So I'm very thankful for your attention. Thank you very much.
Thank you very much. Okay, one question, still an opportunity to ask before lunch.
Yes, I got one question.
Yeah,
Yes.
it looks like no questions. Yeah, thank you. Then thank you indeed for a very interesting very interesting presentation and invitation. And
Announcement for technical.
Arnold's for announcement. Yeah, the floor is yours.
Firstly, good appetit. Thank you for your contributions this morning. But additionally, in case you manage more shorter than 1 hour for your lunch, there's a poster session in the next floor upwards. We have strong team of our young colleagues who are managing this poster session. You can capture first images about posters inside before poster session starts after plenary.
Tas jau nav vērts. Nedūšais, kas nav pagaidzi.